Hello everyone, my name is Aruhi and welcome to my channel. So guys, in my today's video we will learn how to implement GAN networks. So GANs are powerful tool that can create entirely new data that does not exist. And in this tutorial I'll show you how to train a GAN network to generate realistic human faces. So once the model is trained, it will be able to create new faces that does not exist in reality. So guys, whenever we want to work with any AI model, so we need dataset, right? To train any AI model, we need dataset. So for this task also, if you want to train your model to generate entirely new faces, human faces, for that, you need a dataset to train your model first, and GAN network will analyze this data, it will learn pattern from it, and eventually it will generate completely new realistic faces. So for this tutorial, the dataset which I'm using is CelebA dataset. CelebA dataset means celebrity faces dataset. This dataset is available on internet. Let me show you this dataset first. Let's understand what kind of images are there, what kind of dataset is this, and then how we are going to use this dataset for training our GAN network. Open browser, and here this is the URL. And you will hit enter, and from here you can download this dataset. I have mentioned the link of this dataset in my description section. You just copy the link from there, paste on any browser, you'll see this kind of screen. Click on download anyway. When you'll click on downloads anyway, so on this side you'll see that under downloads the download will start. See, the download has been started. So I have already downloaded this dataset, so I'm stopping it, and now I'm going to show you the downloads folder. Let's open downloads folder, and here is the dataset. You will get this kind of zip file. You will unzip it and then just create one folder where you are going to write your code for GAN network. So let's say in my D drive, and in this GANs_env folder, let's create one folder. I've given the name demo. Just create any folder. Inside this demo folder, I'm pasting the data, this data, the downloaded data. Go to the demo folder, paste this file, and then extract this file. After performing the extraction step, you will see this kind of folder. Open this folder. Inside that you have another folder with the same name. Open it, and here you can see the images. Here you'll note that we have the images of different celebrities, and we are only having faces. See, and in every image there is a different kind of face expression. Lighting conditions are different, right? But we only have faces. Why we are only having faces in these images? Because we want to train the GAN network to generate faces only, new faces only, right? So if you want to train your model to generate faces only, that means you need to provide the related data set. You need to provide the images of the faces only. So for that we have this data set, and there is no annotation or anything like that. You just need to have these kind of images. So let's say if you don't want to generate faces using GAN network, you want to generate some different sort of classes or objects, then you will create one folder, right? And inside that folder put the images. You need lots of images, because when you want to train your GAN model to generate any new data, so you need a huge data set first to provide to GAN network so that it can get a proper training to generate such kind of data. Now we have our data set. Now let's understand how to generate images using GAN network. And before moving to that part, another important thing is to install all the required modules which are needed to run this GAN network. So the first thing is to install PyTorch and Torch Vision and Torch Audio. So guys, whenever you want to install PyTorch, Torch Vision and Torch Audio, and let's say if you have a GPU, NVIDIA GPU, and you want to use the power of your GPU to train your GAN network, then your PyTorch should be compiled with CUDA. So you always install PyTorch as per the version of your CUDA. So check the CUDA version first. So how you can check the CUDA version? just go to C drive, and here you will see the program files, and then scroll down and you will see NVIDIA GPU Computing Toolkit. Click here, click on CUDA, and here you will see the version of CUDA which you have installed. So in my case it's 12.4. So my laptop have CUDA version 12.4. So now when I want to install the PyTorch, I will install the PyTorch using CUDA 12.4. Let me show you how. Here we were, right, download PyTorch and open this first link. So scroll down here. See, PyTorch latest version is 2.5.1. If you are working on a Linux machine, click on this. If you are working on Mac, click on this. In my case, I'm working on Windows, so I have selected this one. And then these are the different package managers, means using which package manager you want to install the PyTorch. So we want to install using pip. So pip is selected. And then we are working with Python, so click on Python. And here are the versions of CUDA. See, you can install PyTorch 2.5.1 only with CUDA 11.8, 12.1 or 12.4 if you are using GPU. Let's say you don't have a GPU in your laptop and you want to use CPU, then click on CPU. And if you have a GPU, then you have to check which CUDA version out of these 3 CUDA versions, which CUDA version is installed over here. So you will see which CUDA version is installed here. So in my case, it's 12.4. So I'll go here. I will select 12.4 CUDA, and then you will get a command over here. Copy this command from here. Go to the CMD, open command prompt, and here you will paste the command and it will get installed. So this is the first requirement. And let's say if you have CUDA 12.1, click on this, copy this command, and let's say you want to install it with CPU, then click on this and copy this command from here and then paste on the command prompt. Okay, then paste over here and then hit enter. So this is how you will install. And guys, one more thing, you are not seeing any folder over here. So that means you don't have CUDA installed. So you need to first install the CUDA, and to know how to install CUDA, I have a separate tutorial. Link is given in description section. You can check that tutorial, and following that tutorial, you can successfully install CUDA on your machines first, and then you can follow the further next the tutorial from here. Okay, so this was the first requirement. After that, we need some more packages. So these are the packages, matplotlib and numpy. You can install it like this. Over here, just write it like this and hit enter. These modules will be installed. And after that, if you don't have Jupyter Notebook installed, you will install Jupyter Notebook also, because in my today's tutorial, I'm going to show you the entire code on Jupyter Notebook. So you can install Jupyter Notebook like this, pip install Jupyter Notebook and then hit enter. So in my case, guys, I have created a separate environment for the entire task. So in D drive, I have a folder with the name of GANs_env, and here I have created a separate environment with the name of my env. So see, you have two options over here. One thing is you have Python installed in your PC. You don't want to create any separate environment. Just execute the commands which I've shown you over there and your setup will be ready. Okay. But I always recommend to work in a separate environment. So to create a separate environment, if you want to work under a separate environment, so you first need to create the separate environment. And how you create the separate environment? See here. First is, this is the line using which you can create separate environment. This is the line with which you will activate the environment. And then this is how I installed PyTorch, Torch Vision and Torch Audio using CUDA 12.4. After that, I have installed matplotlib and numpy. And after that, using this command, I have installed Jupyter Notebook, pip install Jupyter Notebook. So this is how you will install all the packages. And now let me activate the environment. So this is my environment name. Let me activate the environment first. So my code is in D drive. See, Here it is in D drive. Under D drive we have this folder, so CD. Now I'll activate the environment. This is the environment name, and this is how you activate the environment. Once you activate the environment, you will see this environment name over here. Now let's open a Jupyter notebook to write the code. So to open the Jupyter notebook, you will write Jupyter space notebook and hit enter. Jupyter notebook will be opened. See, this is the Jupyter notebook, and this is the demo folder we have created, right? And inside this demo folder, okay. So inside this demo folder, we have this zip file, and then we have extracted that zip file. All right. Now here I'll create a Jupyter notebook where we are going to write our today's code. So new Python 3. Over here we are going to write the code now. First, let me show you the versions of the modules which I'm using. So the Python version is 3.10.9. After that, let's see the Torch version. So this is the Torch version, PyTorch 2.5.1, and it is compiled with CUDA 12.4. And now let's see the GPU which is getting used. So for this tutorial, I'm using NVIDIA G4 RTX 4080 laptop GPU. Now let's write a code to load the dataset, right? So we have a folder and we have images in that folder. So this is a folder, right? And in this folder, we have images in it. Now we want to provide these images to the model. So we need to write some sort of code so that we can load the data which is in this folder. We have almost more than 2 lakh images over here. So we want to send these images to the model in batches so that our model can load all these images, right? So that it can get training on it. So we need to write some sort of code for that. Let's see how to do that. So I wrote this function class over here. First, I'm importing all the required modules, and this is the dataset link from where we have downloaded the dataset, right? And then I've created a class. This class I have created, and in this class here, see, root directory. Root directory, here we will provide the path of the folder where our images are. So in our case, where our images are in D drive. In D drive we have this folder, and then demo folder, then this folder, and inside that we have this folder. Here we have all the images. So that path we will provide over here, and then we will also perform some transformations on the images which are present in our dataset folder, right? Transformation means, let's say we want to resize the images, we want to crop the images, we want to perform any sort of data augmentation. All those transformations will perform. I'll show you in this part in detail, okay, after some time. So we are loading all the images, we will perform all the transformations on it, and then we are saving those images in a list. All the names of all the images we are saving in a list. So any image which is ending with .jpg extension, we are saving that image in a list with the name of, this is the list name, okay? And then over here we are just checking the length of the images, means how many images are there in a folder, that we are getting over here. The images which are present in this list, okay, so we are getting the length of that. And after that, see here, we are reading all the images from that list, image path list, and we are converting all the images to RGB, and then we are applying transformations on the images, and finally you will have the image with the image which is acceptable by our model. Okay, so we have created this function. Now in next cell I'll show you how to use this function, how to provide the path of our data set, and then the further steps. So this is the step C. We have mentioned the transform variable. In this variable, we have written all those transformations which we want to apply on the images of our dataset. So first we want to resize all the images to this size. Why we are resizing all the images to 64 into 64 size? Because in the original paper of GAN, the very first paper of GAN, over there they generated the image of size 64 into 64 into 3 size, right? Height and width of the image is 64 into 64, and those were colored images. So in our today's tutorial also, we will generate the fake images of size 64 into 64 into 3. So for that, what we are doing is, we are first, the training data which we are going to give to our model, we are also resizing all those images to size 64 into 64. If you want your model to generate the images of size 64 into 64, so for that, it is always best practice to provide the images to your model while training of same size. Then you will get better results. So that's why whatever images we have over here, see right now the image size is 178 into 218. Every image is of this size. So we want to resize these images to 64 into 64. So that's what we are doing. We are resizing all the images to size 64 into 64. Then we are performing center crop. Center crop means we'll get the center of the image, and then we are converting all the images to tensor, PyTorch tensor. Why we are converting all the images to PyTorch tensor? Because today's tutorial we are using PyTorch framework to train our model GAN network, right? So if you are using PyTorch to train your network, that means all the input data should be converted into a PyTorch tensor. Then only that data will be acceptable by PyTorch and you can use it for training. Okay, so that's what I'm doing here. After that, I am normalizing the data, and for normalizing, I'm using 0.5 mean for 3 channels, and this is the standard deviation, which is 0.5 for all the channels. When you use this and this to normalize your data, you will get all the pixel values of all the images in the range of -1 to +1. Means, see how computer sees this data. So as human being, we can see the images like this, but computer don't see the images like this. Computer understand numbers. Means instead of seeing this image like this, computer will read the pixel values. So there are different for every color, so there is going to be some different numeric value. Okay, so from that numeric value, computer understand what is this in this image. Okay, so all the images, for all the images, we have different pixel values, and by writing this line, we are normalizing the pixel values. Means we want all the values in the pixel values in the range of -1 to +1. So that's what we are doing over here. We are performing the normalization. So these are the different transformations which we want to perform on our data set, and we have written all those transformations in a transform variable. Now let's load the data. See, this is the path of our data set. Let me just copy the path. Just copy the path from here, and then you will write that path over here. Here. So this is the path, right? And then we have our dataset in dataset path variable. Now we are calling CelebA a dataset class. This class, we are calling this class. We are providing root directory. What is our dataset root directory? This one, right? So we have provided that, and we want to perform transformations in it. So these are the transformations we have mentioned here in this variable. So we have done that. Okay, so now in dataset variable, we have all our images. Those images are normalized now in this range, and we have applied all the transformations and everything. We have done everything, and now next step is to divide our dataset into batches, because you can't give the entire dataset, this huge dataset over more than 2 lakh images. You can't give that entire dataset at once to your model, because for that you need a huge memory requirement, huge computation requirement. So what we are doing is, we will divide our entire dataset into small batches, and we'll provide batches one by one to the model to train our model. So for that, to divide your dataset into batches and to provide the dataset to model, we use data loaders. So here we are creating a data loader. I have created a data loader variable. and we are calling the data loader. See, from where we are calling the data loader? See, from Torch only we are calling the data loader. So here, data loader, we are providing a dataset. Our dataset is present in dataset variable. So that's what we are providing here. We provided a dataset and we are mentioning that batch size should be 128, means each batch will have 128 images, which means you will give 128 images at once to a model. Once the model get training on that, then the next 128 images will go to the model, and then the next 128 images, until our model received all the around 2 lakh images. And this shuffle true means, see, whenever we want to train our model, we write shuffle true. Shuffle true means that every time whenever you are providing 128 images in a batch to your model epoch wise, in every epoch there should be a different set of images. Okay, so this is how you define your data loader. And here we are just printing the length of dataset, means how many different images are there in a dataset. So hit enter and see. So these many images we have in our dataset. Now the next step is to write the code for generator, and let's see how to do that. So this is my code for generator. That's it, guys, only this much code. So this code will generate the fake human faces. Now let's try to understand this code. So guys, first of all, if you don't know the theoretical concepts like what is generator, how generator work, and what is discriminator, how discriminator work, then I have a separate video. Please check that video first, because then only you will understand my today's tutorial in a better way. Okay, so yeah, let's see this. So generator is a neural network and discriminator is also a neural network. So in GAN network, we are using two separate neural network. One is generator and one is discriminator. Now let's see what are the different layers in generator neural network. So for that, I have created a generator class, and in this generator class, I am mentioning this z_dim equals to 100. So guys, remember I have explained in my GANs theoretical class that generator, the input to generator is a random noise, right? So random noise is of size 100, one-dimensional vector which have 100 values, and this random noise simply means random numbers. Okay, so first we will provide the one-dimensional vector which will have 100 random values, and this random 100 values, random noise, will become the input to the generator. And image channel 3 means we want to create the output image, fake image, and that fake image should be a colored image. So that's why number of channels are 3 RGB. And here we are writing the model layers. Okay, so first layer is linear layer. Linear layer means fully connected layer, and the input to fully connected layer is z_dim, which is this. So input to the first layer is 100 dimensional 1D vector, this, and the output of this will be 256. What is this 256? This 256 simply means one-dimensional vector which will have 256 values. So this 100 simply means this is a lower dimensional space. Lower dimensional means we have less number of values in it, and the goal of generator is to generate a image of size 64 into 64, means height and width of that image should be 64 into 64, and it should be a colored image, right? So it is very difficult to generate a image with very less number of values. So layer by layer, we are going to increase the number of values of this 1D vector. When we have sufficient number of values in this 1D vector, then we will reshape it and we will get some sort of image. Okay, so this is what we want to do. So the input to the first first layer will be 100 dimensional 1D vector, and it will give the output of 1D vector with 256 values. So this is a high dimensional vector now as compared to 100. Now we have 256 values. So dimensions are increasing now. So this is becoming high dimensional vector. So after that we are using the activation function ReLU. So this is the code for first layer. The output of this layer is 256 dimensional vector. After that, next layer is this. So the output of previous layer, which is this, will become the input to the next layer. This is the input to the next layer. And the output of this layer is 512. Now, after the second layer, we are going to have 512 different features. Guys, we can also call it features. What are those 512 values? Those values means they contain some sort of information. They are some sort of features. So using those 512 different features or using those 512 different values, finally we will generate some image at the final step. I'll show you that in some time. So after this second layer, we have a 1D vector. That vector have 512 values now. So it is becoming higher dimensional vector. And then again, we are having some activation function. And then this is the third layer now. In the third layer, again, the output of the previous layer will become the input to the next layer. And this layer will generate, this layer will give us a higher dimensional vector which will have 1024 values. 1024 value means 1024 features. So from 100 random values, initially we were having 100 values in a 1D vector. From that we have created a 1D vector, a higher dimensional 1D vector of which have 1024 features or 1024 values. Now we will reshape this 1D vector in a way so that it can give us an image. It can generate some fake image, right? So, and image size we want is 64 into 64 and the number of channels we want is 3 because we want to generate a colored image. So that's what we are doing over here. See? So the input to this layer is 1024 and this layer will give us this output. 64 into 64 is height and width of the image. Image channels, we have mentioned it over here, and so we are getting 3, right? So once you have an image here, after this step we will have an image and the size of that image will be 64 into 64 into 3. Now guys, after that, here we are applying a different activation function. You'll see that in above layers we are using ReLU activation function, but after this layer we are using TANH activation function. Why? Now TANH activation function means you will get the pixel values of image, the image which we have generated over here, the pixel values of that fake generated image should lie between -1 to +1. And why we want that? Because if you'll see above, when we were performing the transformation on our training data, here we have applied the normalization method, and I've told you that this normalization method will give you the pixel values of all the images in the range of -1 to +1, right? So we want that our generated, fake generated data, fake generated image by the generator should also have the pixels value in the range which our training data have, right? So that it will be easier for generator to fool the discriminator at later steps. So that's why we use TANH function, so that the generated image should be in the range of -1 to +1, as our training data is in the range of -1 to +1. So this is a model now. These are the layer of a model. So then we have a forward function in the generator class. Here we are calling this model, the model which we have defined above. We are providing Z to it. Z, guys, again, if you have seen my previous video, there I've told you that we are using Z variable for a random noise. So this Z is a 1D vector, and that 1D vector have 100 different values, random noise, random values. that will go to the model, and this is what the model will give us. Model will create our image, and the size of that image will be 64 into 64 into 3, and this part over here tells us about the batch size, right? And finally we'll get the image. So this is the code of generator. That's it, guys. Now let's write the code of discriminator, and then let's try to train a model. Let's run it. So this is the code of discriminator. See, this much, that's it. So again, I'm creating a class, discriminator class, and here I have written the layers, different layers which are there in our discriminator model. So first we are using the flatten layer. After that we are using this layer, first layer. This is the second layer, and then this is the third layer, and this is the fourth layer, and this final activation function will give us the output. Now let's try to understand what is happening here. See, first thing is discriminator is also a neural network, right? So the output of generator, so this is the fake image which is generated by the generator. This will become the input to the discriminator. So, and the size of this image is 64 into 64 into 3, and batch size also. This will go to the discriminator. So let's see that. So first we are using flatten layer. Why we are using flatten layer? Because over here the output of the generator is this. How many values we have? 1, 2, 3 and 4. This is a 4D tensor, but this is we need to convert this to a 1D vector, then only discriminator will accept the data. Okay, always remember, you can't give image as it is, the generated image which is generated by the generator. You can't provide that image as it is to the discriminator. You need to flatten that image, then only discriminator will work on that image and finally will give us the output. Okay, so that's what we are doing. So this thing is getting flattened over here, and after that, once you flatten that image, so this is the input. So what is the input? The output of the generator. This is the output of the generator. That is becoming the input to the discriminator. And the output of the first layer of the discriminator is this 1024. What does this mean? This means that this layer will give you 1024 features, means 1024 values, right? Feature simply means every value will have some sort of information about some feature of the image, right? So we can call it 102 features, or we can call 1024 values. Okay, we are applying this activation function on it. Then the output of previous layer is this. It will become the input to the next layer, and in next layer the input is 1024, but this layer is reducing it to 512. So you're going to have 512 neurons over here, and every neuron will store some sort of information, right? And then after that, the 512, which is the output of this layer, will become the input to the next layer, and the next layer is reducing that 256. See guys, the task of discriminator is to classify that the image which is given to the discriminator is fake or real. So discriminator will give you a probability value. If the probability value is 0 or closer to 0, that means discriminator is saying this image is fake. And if the probability value which discriminator gave us is closer to 1 or 1, that means discriminator is saying this image is a real image. So discriminator will give you a probability value between 0 to 1. The values closer to 0 means discriminator is saying fake image, and the value closer to 1 means discriminator is saying that this is a real image. So this is the ultimate goal. So for that, what we are doing is layer by layer, we are reducing the number of values in a 1D vector, so that in a final layer discriminator will only have one value. Okay, so that's why you'll notice that every layer, first we have 1024 value in 1D vector, then we have 512 value, then we have 256 values, and in final layer we are only having one value, right? So the previous layer output is this, which become the input to the discriminator, and the last layer of the discriminator is providing us only one value. Now once we have this one value, we are applying sigmoid activation function on it. Now why we are using sigmoid activation function? Because as I've told you that discriminator will give you a probability value. Now the value which we have over here after the final layer is not a probability value. Now we want to convert that value into the form of a probability. So that's why we used sigmoid activation function on it. Sigmoid activation function is used for binary classification problem. So we use the sigmoid activation function and we will get a probability value. That probability value will lie between 0 to 1, and I've told you already 0 means the fake image and 1 means the real image. So this is how discriminator will work. Then we have a forward function and we are applying the model. This model, we are providing the image of the generator to it and the model will work on it. So this is how discriminator work. Now we have the code for generator and discriminator. Now we will need to define the parameters like the learning rate and the other parameters which are required to train the model, and which loss function we want to use to calculate the loss. Because what we want the generator to generate realistic images, new realistic images. And how we do that? For that we need to train the model for many epochs, and epoch by epoch we calculate the loss, and on the basis of that loss function, on the basis of the loss, we improve our generator and discriminator, right? So all that part we need to do now. So let's see how to do that. So here, this is the loss function we are going to use. I have created a variable with the name of adversarial loss, and here I'm using this loss function. BCE loss means binary cross entropy loss. Why we are using this function? Because discriminator is a binary classifier which will tell the image is fake or real. So for that we will use this activation function. And here we are calling the generator class. In generator variable, I'm calling the generator class. See, this is the name of the generator class now. See here, generator. That's what I'm calling here, generator, and the input to generator is 1D vector which have 100 values, random noise. Then in discriminator variable, I'm calling the discriminator class. Here optimizer underscore G means the optimizer for generator class. Optimizer underscore D means optimizer for discriminator class. Why we need optimizers, guys? See, with the help of optimizers only, optimizer basically help us to update the weights, right? So I am using Adam optimizer for discriminator and generator, and this is the learning rate I'm using for both the models. You can change it and you can see what kind of outputs you get. But in my tutorial, I have tried various different learning rates, and this learning rate was giving me better results as compared to other learning rates. So that's why I've used this one. Beta's values are these. After that, this line simply means this. The purpose of writing this line is that if you have a GPU in your PC or laptop, obviously you should use the power of the GPU, so the training will be fast, right? So the line here means if GPU is available, use GPU, otherwise use CPU. So we are sending our generator to device, means if GPU is available, use send the generator code to GPU, otherwise you send it to CPU. In the same way, if GPU is available, then send discriminator to GPU, otherwise let it be on CPU. So let's run it. So these are the important parameters we have defined. Now let's write a function which will train the generator, which will train the discriminator, which will calculate the loss, and it will show you the fake generated images. Let's see that. This is the code. I have this function. Generator parameters are, you'll provide the generator class to it, discriminator class to it, data loader also. Why data loader? Because we want to train the model on batches of data. So that's what we are doing. Data loader, we have defined the data loader. If you see above, see we have created the data loader and we have defined the batch size is 128. So guys, we have these many images in our data set, and if you divide it with 128, you will get 1500 something value. That means for each epoch you're going to have around 1500 different batches. Okay, so now here we want to run the model for several epochs, so this for loop is for that. So if the epoch size is 5, so this loop will work for 5 times, and for every loop we are loading the data from data loaders, means we are loading the data into batches, and the batch size is 128. Real images, see, this real images means the images of our data set. See guys, how will discriminator get to know which one is real images and which one is fake image generated by the generator? So for that we have a data set, right, using which we are training a model. So our images from our data set, the data set which we are using to train our model, that those images are present in real underscore images variable, right? Real images means the images of our data set, and we are sending the images to device. What does this means? See, here we have defined that if GPU is available, send the generator to GPU, otherwise on CPU. Same, if GPU is available, send the discriminator to GPU, otherwise on CPU. Your images should be on same device where your generator and discriminator is. So that's why we wrote like this. And then this is for batch size. And then we have valid variable. And here we are having a tensor with one value. See what is happening here. So these are the images, right? And these are the images from our data set. So these are the real images. These are not fake images, right? These are the training images from our data set. So for these images, we are creating a tensor with torch.once, means we will have a list with, suppose there are 128 images in a batches. Okay, let's understand this with example. So suppose, for now, suppose the batch size is, let's say the batch size is 4, means at one time 4 images will go to the model for training. So suppose these are the 4 images, right? These are the 4 images. Now for these are real images from our data set. These are real images from our data set. Now for these 4 images, now I have created a variable with the name of valid, and there I'm using torch.tensors once. That means 1, 1, 1, 1. So for this image, we are saying the label is 1. For this, the probability value is 1. For this, the probability value is 1. For this also, the probability value is 1. And I've told you that discriminator gives us what discriminator does. So discriminator will give us the probability value between 0 to 1. 1 means real image, 0 means the fake image by generator. All right. So when we are providing the data to the model with the real images, we provide this list, this tensor. With real data, we are providing 1, 1, 1. That means we are telling our model that these kind of images which are from our real data set, for them, these are the labels. And let's go back to the code again. Where is it? Here. And see, I have another tensor with the name of fake, where I'm using torch.zeros. Torch.zeros. In valid, we were using torch.ones. Torch.zeros means we have a fake variable over here, and here I have created this list, right? So this is for the fake images. Now let's go back to the code. Let's try to understand here. First, we are optimizer underscore D means discriminators optimizer. Real loss means when we are trying to calculate the loss of discriminator for images which are there in our data set, the real images which we are using to train our model. So for that, we are calculating the discriminator loss in real loss, and we are calling our loss function, the loss function which we have defined here. Remember this nn.bce loss. Discriminator, we are providing real images which are there in our discriminator. We are providing real images of our data set to the discriminator with this valid, with ones. What it means is we want to train here discriminator, and we are telling discriminator that for these images, these are the labels. And when we are trying to calculate the loss of discriminator, when we are providing fake images to the discriminator, that part we are doing in this fake underscore loss. So this is the adversarial loss function, same function. We are applying discriminator on. This is the image generated by the generator. So what generator will give us? Generator will give us the fake image, and we write that this 100 simply means the input to the generator will be the 100 random noise which have 100 values, and generator will generate an image on it, and that will go to the discriminator, and with that we are providing the labels which are present in this fake. Okay, so then the real loss plus fake loss divided by 2 will give you the discriminator loss. Now let me explain you with example. So let's say that here I'm writing, okay, so these are the labels which we have provided. Now suppose the output of the discriminator is this 0.9, 0.6, 0.8, 0.9. So let's say this is the output of discriminator, and these are the labels which we have sent. So we have mentioned here 1, and the output of the generator discriminator is this for the first image of a batch. For second image of the batch, this is the output of the discriminator 0.6. For the third image of the batch, this is the probability value which discriminator gave, and this is the fourth image of the batch, and this is the value which discriminator gave us. Now how far these images are from the values which are here in valid list, right? So we will see the difference between the probability value which discriminator predicted, which is this, right? And these are the valid which we have provided. Now how far the predicted value is from the list which we have provided, and this is how we will get the loss on real images. In the same way, for the fake images also, let's say this is the list we have provided 0, 0, 0 and 0 for the batch of images, and these are the predictions 0.2, 0.4, 0.3 and 0.1. So let's say these are the predictions, probability values by the discriminator, and these are the values which we have provided with the fake images, because 0 means the fake image, 1 means the real image. So whenever we are providing the fake image to the discriminator, we want to send 0 labels with it. Now loss function will see how far the output probability value is from the value which we have provided, how far this 0.4 is from this 0, how far is the 0.3 is from this 0, and how far is 0.1 from this 0. And on the basis of that, we'll get the loss value. Then we will add the values. Then we will add the real loss and the fake loss, and divided by 2 you will get the discriminator loss, and then we are using the optimizer in back propagation to update the weights. So this is how we this is how we train the discriminator. See, this much. Got it? And then this is how we train the generator. We are using the optimizer underscore G, means the optimizer for generator. We are calculating the loss function. How we calculate the loss function of generator? See, generator depends upon the feedback of the discriminator. So the discriminator will give the feedback to generator, and then generator improves it. So see that the loss function, discriminator, when we provided this random noise to the discriminator calculated the loss on it. Valid means the torch dot tensors with one value. This is how we calculate the generator loss. And after calculating the generator loss in backward propagation, in backward pass, we try to update the weights, and then we train the model again, right? And then here, see, this line will show you the discriminator loss and generator loss after every 50 batches, because for every epoch, when we are training a model, for every epoch we are going to have around 1500 batches, because we have around 2 lakh images and our batch size is 128. If you'll divide this 2 lakh value with 128, you will get around 1500 batches. So for every batch, for every epoch, model will see all the batches, okay, and will train the model. Let me show you. So basically I have this training over here. Okay, not here, wait. So I have performed the training already, so that because it's a lengthy process and it will take time. So you can see here, see, epoch 0, I'm training the model for 10 epochs. Batch 0, we have 1583 batches. For the first batch in epoch 0, 0th batch, this is the discriminator loss and this is the generator loss. And then after 50, this is the 50th batch. I'm not showing the output of all the batches. So after 0th batch, batch number 50 of epoch 0 only, this is the discriminator loss and this is the generator loss. Guys, here you will note one thing, that the generator loss is high and the discriminator loss is low. Why? Because when you'll start the training GAN network, at initial epochs, generator will not generate a good image and discriminator will easily identify whether it is a fake image or a real image, right? So that's why the loss of discriminator is low, because discriminator is able to find out very easily whether it is a fake image or a real image, but the generator loss is high. So see, here you can see, after running all the batches in epoch 0, this is the this discriminator loss and this is the generator loss, and these are the phases our generator generated after the first epoch. See, right now we are not getting good phases, right? So these are the totally new phases. These phases do not exist. This kind of output you get from generator after first epoch. Then now we are training for next epoch. Again, we are running all the batches, right? And this is the output. These are the phases generated by the generator after the second epoch. And then the third epoch, these are the phases we are getting after that epoch. And then we train the model for next epoch, and these are the phases we are getting. So like this, you will train your model for multiple epochs. You will stop the training after that time when you're seeing that the images generated by the generator are realistic enough. At the time you can stop the training. So once you train the model to generate fake images, you only need generator. You don't need discriminator anymore. Why? because discriminator is only used to improve the generator. On the basis of discriminator feedback, our generator improves itself. But once you have a generator which is giving you good generated data, you don't need discriminator anymore. You only want to generate fake images, fake data. So for that, generator will be used. So using generator, you can then generate the fake data. So guys, this is how you can train your model. So link of the code is given in description section. I hope this video is helpful. And guys, if you like my content, please like, share and subscribe my channel. Thank you for watching.